Right, this is Lepton, and it's question 1. So let's get stuck in. This definition we're given here, it says, is wrong. So write down the words that should replace the words in italics. The wavelength of a progressive wave is the distance between two successive points which are oscillating with the same amplitude. So in a progressive wave, all the points oscillate with the same amplitude, so this is very wrong. What it should read is between successive points that are oscillating in phase with each other. So in phase is the key word here that we're going to get marks for. Explain why the original version does not make sense. Well, it's what I've said really. So we just want to say that in progressive waves, all points oscillate with the same amplitude. So what they're examining here is the misconception that's quite common in students where they mix up amplitude and displacement. So if we look along the wave, the displacement is different everywhere. Well, in cycles, but the amplitude is the same. Okay, the top diagram is a plan view from above showing the position of crests of a wave at time t equals 0, and then we've got the vertical section of the water also at time t equals 0. So these sort of line up with the crests there. That's fine. And by t equals 12 seconds, the wave has traveled this far. The wavelength is this, calculate the frequency. So what we're looking to do is use the time and the distance to get the speed. So distance divided by time. 60 times 10 to the minus 3 divided by time, 0.12. So what is that, 0.5 meters per second. And then we can use the wave equation, c equals f lambda. Frequency is what we're trying to find, so let's rearrange that for frequency. That was c over lambda. So 0.5 divided by the wavelength, 0.015. So what is that? That's 0.1 over 0.03. That's 33. Sorry, 0.3 hertz. On the top diagram, drawing the positions of the crests at t equals 0.01 seconds. So if we think about what the time period of this wave is, that's easiest done actually looking at the question before. When t is 0.12 seconds, it has traveled 4 whole wavelengths, so the time period is 1/4 of that. So or 1 over frequency, I suppose 1 divided by 33.3 is going to give us the same thing, which implies that 0.01 seconds is 1/3 of a cycle. So these crests will have moved 1/3 of a wavelength along. So we need to draw that in reasonably carefully. I'm going to call that about 1/3 of the way along. I mean, obviously, if I was actually sitting the exam, I'd probably whip out the ruler and just take a measurement and make sure that I am splitting this up in the ratio 1:2 to make sure that they are 1/3 of the way along. You guys should definitely do that. I'm not going to bother in this run through. Okay, so part C, it looks like we're about to see some sort of diffraction pattern. We've got a double slit arrangement. Interference pattern is observed. The diagram is not to scale. That's fine. Making use of the equation for double slit interference, determine whether there is constructive or destructive interference at point P. Give your reasoning. So the equation that we're looking for is the lambda equals AY over D. And we have We've got the wavelength from before. The wavelength is 15 millimeters. I'm assuming these are the same waves. Yeah, no other wavelength. Oh, yeah, we're given right here. So 15 millimeters. We've got our A is the space between the slits here, so 80 millimeters. D is 320 millimeters. We're looking to see whether y equals 30 millimeters will give us the correct thing. So let's rearrange this for y. So lambda d over a, let's fill in the numbers. 15 millimeters multiplied by 320 millimeters divided by 80 millimeters equals 60 millimeters. So the point P is actually halfway between two maxima, and therefore it is a minima, so destructive interference. So that hopefully gets us all 3 marks. Notice that I kept everything in millimeters there, and that's okay to do. If you look at this equation, if I multiply both sides here by d, I've got lambda d equals ay. I've got 2 lengths, the product of 2 lengths equal to the product of 2 lengths. If I keep everything in the same unit, this equation is still absolutely valid. So it's okay to do that as long as you are consistent then. Explain why diffraction is essential for the formation of the interference pattern. So for interference, the waves need to overlap, and they can only do that if they spread out from the slits. So I guess we write that as diffraction causes spreading from slits, which allows the waves to overlap. And having answered questions of this type before, my suspicion is our 2 marks are 1 for saying that the diffraction causes spreading, and the second for saying that the waves need to overlap. Yeah, so I think that's it. That's question 1 then, done.